I'll just try to share my screen. Okay. Can you see my screen now?
Yeah, I can see your screen.
And also the laser pointer?
Yeah. Yeah.
Okay. All right. Okay. That usually doesn't work so smoothly, but um, all right. Well, again, thank you for the introduction. And oh wait, actually, I forgot. I did put my video on. Just do that. Sorry, just 1 second. I think you can see me now. Right.
Yeah, I can see you.
All right. So I'll do this again.
I can see your screen and move your laser pointer. Yeah, it's moving. It's moving.
Okay, perfect. Okay. All right. Yeah. Thank you for the introduction, Pratyasha, and thank you so much for the opportunity to talk about this. And today, what I want to talk about is essentially, at least we call the webinar synergies between high voltage and high power in today's world. And yeah, I'm Mathew, as Pratyasha mentioned, and the talk today would essentially go through my career so far. Uh, I've only been working for about 2 years now, and hopefully in the process, kind of highlight certain new fields that are popping up in the power industry today and also for the future, which might be of interest for people pursuing their PhD right now and looking for a job later in the industry. All right, so just to give an overview of my presentation, I will first start with a short introduction about my career so far, what have been the main goals and motivation when making each career step. And I'd like to share 3 key experiences with all of you. So this was my time at Prysmian, my master thesis at Delft, and right now what I work on at Hitachi HVDC. And finally, I'd like to wrap up with some reflections, hopefully share some lessons learned. And yeah, if it gets a bit confusing, you can always keep track at the bottom. In the presentation, I've kept these beads at the top, bottom. So I think we can start with the first one, my career so far. So I decided just to take a map and show. So I started with my bachelor's in NIT Surathkal. I did my bachelor's in electrical and electronics. I worked a lot, mostly on, I would say, power system level stuff. So control and protection schemes for microgrids. I then went to IIT Delhi and I researched the application of DC microgrids to spread electricity access in rural areas, such as in the middle of deserts, to make them electricity independent. Sorry. And then after that, I moved to the Netherlands to do my master's in power engineering. And here I specialize mainly in high voltage and some of power electronics. Also at Delft, I did an internship and later worked part-time at Prysmian. And my work here was mainly to do with high voltage cable joints, even cables and cable accessories, connectors, terminations, stuff like that. After completing my master's, I moved to Ludvika, Sweden. It's a small city in the middle of nowhere, I would say. But I'll get back to why I moved here and why Ludvika is quite important in today's world. And actually, in September, I will then shift to Switzerland. I'll be working at CERN, and this would be high power converters for particle accelerator systems. And this is essentially the magnets that they have in particle accelerators to accelerate the beam and change the direction of the beam. I would be working on those kind of converters. So yeah, so this is essentially an overview of what I've been doing so far. And to talk about essentially my main goals and motivation and the reason why I've been moving around so much is threefold, I would say. So the first is obviously I want to perform impactful research. And how I check this is by continuously asking myself the question, do I know the final product or application, or where is this knowledge going to be used in the world? And I keep asking myself that question. And if I can't answer it, then I have to rethink what I'm doing. The second is to learn different work cultures. Going around Europe, also in India, I've seen that different places, different people have a lot of different work cultures. And I keep asking myself, how can I take the best out of each person that I've met and improve my own work ethic? And the final thing that I'd like to also talk about in this talk is about front loading my career path and how this has also helped me in research. I'll get back to, but this is essentially asking myself, what else can I do right now? Can I be doing something else in parallel? Can I also be exploring something else? Or, and that helps me really broaden my mindset. So the first thing I can talk about is basically my time at Prismian. Now, I can't go much into detail because a lot of it is confidential, but I can give an overview of what I learned at Prismian and how it was very helpful in me in understanding what I'd like to do in the future. So this was during my master in TU Delft, and Prismian has an R&D center, quite a big R&D center in Delft itself. A lot of you might actually already know. And I worked at the R&D department for high voltage network components. It's called NWC. And my main project was essentially a click fit cable joint. And the click fit concept, so apart from Prismian, a lot of competitors, their cable joints essentially already manufactured together, or they need to be jointed on the field. But Prismian has this concept called the click fit concept, where essentially you take a cable joint and you click one side of one end of the cable, click another end of the cable, and essentially it's very simple on field to assemble such a cable joint. Now, my topic was not just any cable joint. It was sort of a cable joint of cable joints. And this was essentially when you have a cable, when you have two cables and you have a joint, and the joint is, let's say, goes bad or needs to be replaced, you essentially cut the cable joint out of the cable section. But now you're left with two cables that are really far apart. And for that, you need something what Prismian called an XL joint of sorts. So this was a longer cable joint, and it was almost twice in length. And this posed a lot of issues with related to thermal stresses, as well as from the assembly point of view. So my job, let's say, was essentially to first design the cable joint itself. And we already had the designs from previous cable joints, but I had to make this combined cable joint for the first time. And after designing it, essentially I had to optimize the design with respect to electric field stresses, thermal stresses, assembly point of view, and also testing. Finally, I had to take part in laboratory IEC tests. So this was according to IEC 60840. And then also work on future suitability. So the same cable joint, how would it change for cables of, let's say, different diameters, different, you have aluminum and copper, and finding out the suitability of this product with a wide range of different cables. So the project workflow was essentially, so on one hand, I built three kinds of models. So there was a 2D model, a 2D axisymmetric model, and a 3D model. I ended up not using the 3D model because there were some issues towards the end, but this was all in AutoCAD. And then I essentially imported them into COMSOL multiphysics and then studied different behaviors. So the first thing was 2D axisymmetric with an electrostatic study at steady state. I studied the electric field distribution, tangential and normal. at different parts of the cable joint. And then I made some improvements, and you can see here that it essentially reduces the electric field stresses. And this was the first layer of design optimization. The second was a electromagnetic heating study, which is a multi-physics. So it couples electric currents and the heat physics. And at steady state, essentially, the cable system that I had to design for, I first determined the ampacity for it. I can't share what the ampacity was because that's confidential, but you find out what the ampacity of the cable system is, and then you go back to the axis symmetric model of the cable joint, pass the same current through it, and check if your XLP is at 90 degrees, which is the ampacity, and then study the temperature distribution within the cable joint. And this was first done at steady state, and then make some kind of improvements to the design, better allow the heat to dissipate. And then finally, with a time-dependent study, we essentially simulated the IEC 60840 test. So this is essentially 24 hours. The first 8 hours are heating it to, I think, 5 to 10 degrees above the design capability. Maintain that temperature for 2 hours, and then allow the cable or the cable joint to cool for 16 hours. And this was essentially the input current of sorts. This was the temperature it reaches in the cable. And then finally, these were some of the temperatures it reached within the cable joint. So you can see it's much hotter than the cable itself. And I can't say what these were, but essentially there were some improvements that were made. And that really helped bringing down the operating temperatures of these cable joints, and thereby also increasing lifetime, reliability, a lot of different parameters. I also worked on some other projects while I was at Prysmian, and this involved dry type, wet type terminations, outdoor terminations, some connectors, some stress cones. And essentially Prysmian was a really good time for me to learn about the R&D workflow at a high voltage manufacturer. And this gave me like a good insight into what I would like to do also in the future. R&D was very exciting. So, but for my thesis, which is the next subsection, I wanted to come back to TU Delft and really do something research intensive, purely academic of sorts. And my thesis was essentially titled Pulse Staging of Oil Paper. And I can start by talking about what the project context was. So the context begins with understanding what our power grid looks like today. It looks something like this. You have generation, transmission, distribution. But as you all know, with the rapid energy transition, there's an increasing penetration of powertronic interfaces at various parts of the grid. This can be generation, this can be compensation like FACS or STATCOMs. It could also be conversion like solid state transformers. And what is really accelerating this penetration, I would say, is essentially the development of new semiconductors like silicon carbide that keep pushing the limits. So previously, semiconductors, I would say, were limited to lower voltages, but now they're kind of creeping into the medium voltage and high voltage domain. And this essentially causes a lot of different outcomes, what I studied in my literature review. Because now we have, instead of smooth conventional AC waveforms, we now have repeated switching. And these cause pulsed stresses on the insulations of these power equipment. And when I was looking through the common ranges of such waveforms, from literature, we all know that essentially peak voltage amplitude and the frequency severely degrade lifetime. And what my thesis was about was essentially was sparked by seeing that, okay, now we have this kind of transition into more powertronics in the grid. What is the impact of it? Is there something that we missed seeing? So my entire thesis was essentially divided into two parts. The main goal was obviously to investigate the performance of oil paper. Oil paper, because this could be a suitable insulation for solid state transformers under pulsed waveforms. But in order to investigate the performance of this dielectric, I first had to develop a pulse modulator which can produce pulses across capacitive insulations. And we'll get into why this was so complex, because this was previously only done for resistive loads, but capacitive loads significantly complicate the design of such modulators. So first we talk about the development part. So I studied different topologies first. So line type modulator, a simple high voltage switch, a Mach generator, and finally a solid state fed pulse transformer. And when I listed out all the major pros and cons of each type, I finally decided on the solid state fed PT, and PT here stands for pulse transformer. Sorry for not mentioning the acronym anywhere. But also I realized that it would be very sensitive to transformer design. And this was one of the biggest challenges for me in my thesis. So
Philip, Balaji here.
Yes, hi Balaji, yeah.
So I've used I've also tried to implement this D solid state modulator with PT,
Okay.
but there was severe ringing on the secondary side, LC oscillations.
Okay.
Is there a tip on how to overcome that?
Yes, for sure.
So transformer windings, they form a capacitive network with each other.
Yes.
If you have layered winding, so in that case, the capacitance would be severe. Therefore, ringing will happen. So yeah, I see voltage and shape control is a significant problem.
Yes, yeah, I completely agree with that. And I'm happy that you asked this question, because it shows that there is somebody who's faced the same problems. I also had extreme ringing, and I had to come up with different ways to solve it essentially. And I will go through the entire pulse modulator design here. So hopefully that can assist you in your research as well.
Yeah, thanks. So actually, in my opinion, solid state marks would have been a better option.
Yes. So yeah, definitely the other solutions are also good. It's not that one is better, but the major reason why I went for the pulse transformer was essentially considering that my master thesis was only, let's say, 6 to 9 months long. And the people around me already had an expertise in transformer design. So I felt more confident going into pulse transformer. So that's the only reason why I went for this. Obviously, it is possible with Mach generator as well. And also a lot of people have studied with the high voltage switch topologies also. So yeah, but we will go through it. Yeah, no worries. All right. So I mentioned that sensitive transformer design. So why is that? Well, to really keep it like bare bones, essentially, this was one of the waveforms that let's say we synthesized from a pulse transformer, and you can see like a lot of oscillations at the rise time and causing a lot of overshoot as well. But essentially, if you do a frequency spectrum analysis of this, you see that there is a range of frequencies, and regular sinus transformers only need to transmit the fundamental component, which is usually 50 hertz or whatever. And this is relatively simple to do because we had to essentially just pass one frequency, and the bandwidth is more forgiving. But when it comes to pulse transformers, we also have to be able to transmit these other higher frequency components. And this can range to several 0.2 megahertz, like what we see here. And what this essentially means is that when we design pulse transformers, there is a certain bandwidth. So let's keep it at F min, F max. And this bandwidth needs to be maintained in order to ensure correct performance of the pulse transformer. And these bandwidths, obviously in research, nothing comes for free. So the Fmin was essentially limited by the core saturation, and the Fmax was limited by the parasitics of the transformer themselves. So that is L sigma and CD. And this essentially caused a lot of challenges in my research and trying to navigate between these two. And we'll get more into it. So the first thing that I did was essentially try to model a pulse transformer. Now, I already knew that there was an IEEE pulse transformer model. It looks something like this. And essentially what they do is they divide any pulse into 3 time segments or 3 time windows: the leading edge, the pulse stop, and the trailing edge. And you can essentially decouple the transformer, let's say, dynamics in each of these time windows through 3 different models. And also all the elements were referred to the secondary. But for my thesis, because my final goal was testing dielectrics under this pulsed shape, what was important for me was the leading edge. So that is what I focused on. You may also ask that pulse stop can also be significant. It is. And trailing edge is not so significant because I plan to use bipolar pulses. But pulse stop essentially is not really major optimization. It's just a design. You can essentially calculate the ratio of your resistance with your inductance, and you get a time constant. And if that time constant is larger than your actual pulse width, it won't droop much. And that was something that was easy to, let's say, satisfy, at least for me. So I mainly focused on the first time window. And now I zoomed in into this time window, and the 2 major literature that I found was one which is way long back. This was during for the World War. MIT studied a lot of radar systems, and these radar systems essentially had a pulse transformer with a resistive load. And you can see here that this is just, again, the rising edge. So they have L sigma and CD, which models the transformer parasitics. We have a output load and an input resistance, which limits the current and is intrinsic of any kind of source that we might have. And they came up with 2 main equations. The first equation showed that the overshoot depends on the parasitic ratio, which is L sigma divided by CD. And the rise time depends on the parasitic product, which is L sigma into CD. But now it was important to know that this was for our load. But we know that dielectrics are capacitive in nature. So if I wanted to put a capacitive load, the next question would be, what if this load was a C load? Well, when I did the maths, it was easy to see that adding a capacitive load would essentially add to the distributed, the parasitic capacitance of the transformer itself, significantly, I would say, decreasing performance of the output pulse waveform. And I tried this, and it was essentially just became a sine wave again. So there was no pulse. And also another important part to know here is when I prepare a pulse transformer for dielectric testing, it is possible that the C load itself varies, because this depends on what kind of electrodes I use, the number of layers that I put. Maybe I can put 1 or 2 or 3 layers of OIP, and also the material itself. Maybe in the future, I want to test epoxy, and that would have a different epsilon, and epsilon AD of the C load would then again change. So if I were to just directly go with their equations, it would be, first of all, almost sinus. And secondly, it wouldn't scale with different kinds of tests that I wanted to perform. So I had to come up with a solution. And my solution at that time was to essentially do this waveform. Now, first we see, again, the same pulse transformer, L sigma CD. but also I added these test elements, what I called as RT and CT. And the reason for this were again three. The first is it decouples the transformer parasitics from the C load itself uh, by acting as like a barrier. The second is that by varying the values of RT and CT, which is essentially like a filter, we could then tune the overshoot and rise times. And thirdly, or quite important, the R test essentially limits the current after dielectric breakdown happens at CL, because obviously we do breakdown testing and aging testing. At some point, the C load breaks. And that short circuit current can be quite high, and I wanted to be able to limit it. So these were the three
Philip,
main.
one question here. So, but introducing RT wanted reduce the output voltage because you're adding in a resistor and you'll have a drop. And transformer winding itself, when it delivers current, because in the secondary side you'll have a lot of turns.
Yes.
In addition to that resistance, if you add this resistance, the voltage regulation won't it be poor?
Yes. I mean, it would. And definitely there will be some voltage drop across RT. But then when we finally reached C load, we saw that the waveform that we were getting was more than sufficient to perform dielectric testing. And again, I'll show the waveforms that we produced at the very after a bit. And then you can see that it was pretty much sufficient, I would say, to perform dielectric testing. Yeah, and I'll get to that. Thank you for the question, though. So finally, the same kind of exercise, I started deriving what was now a third order equation. I finally got to something like this. And I then defined three parameters, P, Q, and R. And I finally got to what I called the PQR equation. Now, the PQR equation can be quite powerful if used right. But first, what is P, Q, and R? Well, how I saw it was P was essentially the parasitics parameter, which modeled the dynamics of the transformer parasitics. Q was a quality parameter, which allowed us to see the performance of the output waveform. And R was a relational parameter that linked essentially P and Q. And now with a model ready, I could start predicting output waveforms. So I put these differential equations into MATLAB, and I started putting in values for L sigma, CD, C load, RT, and CT, and then started solving the equations for different values. And then I could study the impact of each element on the output waveform. So first, obviously, an increase of parasitics would increase overshoots, which was not good. But at the same time, allowing RT and CT in the circuit gave us the capability of tuning the output waveform. And you can see that changing RT and CT can essentially dampen overshoots to what we would require. I then went a step further and essentially plotted the normalized overshoot and the normalized rise time with respect to the P and Q parameters. And then I saw that, and you can see it here as well on the left and on the right, where the rise time is the lowest, it can also have really high overshoots, which is understandable because it would rise faster, but it would also overstep the test voltage and then have to come back down. But then I defined a performance coefficient, which I called psi PMC, so a pulse modulator coefficient, which essentially is a weighted sum of normalized overshoot and normalized rise time. And setting KV is equal to KT is equal to 1, which means that both rise time and overshoot are equally important to me. When I plotted it across P and Q, I saw that even though there is a lot of trade-offs, there is an optimal line where the psi PMC is quite high. And this, when viewed in 2D, would essentially form what I call then as the psi line, which is essentially the optimized points in the design space where we should try to aim and keep our pulse modulator within. But obviously this was qualitative at that point because we still didn't develop the pulse modulator itself yet. And that is essentially what I will go next to. So yeah, so very close to the seeing the output waveforms, especially for you, Balaji. You can see the challenges that we face, maybe similar to what you have faced as well. The first step that I did was essentially define what my output needed to look like. So I wanted my input to come from AC mains. So let's say around 230 volts. I wanted a maximum test voltage of around 14 to 15 kV peak to peak. And the reason I picked this is because around 7 to 8 kV was sufficient to break down the OIP samples that we had in the lab. So I had to at least have that much. Pulse repetition rate was important because I wanted to vary the frequency from maybe 10 to 50 kilohertz and do tests at each frequency and then understand even the impact of frequency on the pulse staging of the dielectric. The overshoot, like I mentioned, should be very low because dielectric breakdown is extremely sensitive to voltage magnitude. So even slightly higher voltage can cause a completely different breakdown characteristic. And finally, the rise time itself should be at least less than 20% of the entire pulse width. And this was essentially how I defined my pulse. And like I mentioned before, it was a bipolar pulse. And one of the reasons I picked this was to keep pulse transformer design simple to an extent, because having a unipolar pulse, repeated unipolar pulses, would essentially then mean that the transformer core would slowly start saturating. And then I would need what is called a reset circuit, which essentially after a certain duration induces a negative magnetic flux into the core and then reset the saturation. And this was too complex in a 9-month thesis, so I just did not go that route. I went bipolar pulses. So the first thing then I had to do was select a magnetic core, and this was one of the this was the first challenge, I would say. So usually when people make pulse modulators, they want at least, I mean, only one, a single turn primary, let's say. And how they can do this is by keeping repetition rates low and also using iron-based alloys. But in my case, iron-based alloys, which have a good desaturation, also have higher losses, and using this in repeated very high frequencies would cause the core to essentially burn up. So I then had to settle for soft ferrites, which have lower BSAT, but also had lower losses, which was compatible with what I wanted to do. I ended up with a magnesium zinc ferrite. It was a very common ferrite, a U core, which had around 500 millitesla. And this was really low for making a pulse modulator because this severely limits your design space. And when I calculated the minimum number of turns I would need, considering the core that I had, I would need at least 18 turns, which is extremely high for a pulse modulator, because like you also mentioned, Balaji, like if your primary itself is 18 and your turns ratio is 50, that would mean an enormous amount of parasitic capacitance, which would severely degrade output pulse performance. I then had to settle for a sort of 8 core arrangement to increase the AE. This also increased leakage inductance a bit, but it was still in check, let's say. And this brought down the required number of turns to just 5. I ended up using 4, I think. And this was selected, and this was the magnetic core. So this was the first challenge. The second challenge, which I would say was much bigger, was actually designing the winding. This was very complex, and my workflow to start with was essentially designing the bobbins in a CAD software, Fusion 360. I then 3D printed them and then took them to a winding machine that we had in the lab, and then built the transformer, and then did a lot of testing and evaluation. I went through a total of around 20 iterations for primary and secondary winding. You can see here, this is so you can see the designs actually changing. So I started with something like a fin layer. I even tried layered windings like you did, Balaji, but then the output
Actually, we also
performance.
did the same thing. And in addition to this, we resin casted the secondary winding so that it will limit the partial discharge during such high frequency pulses. That
Yeah, I
helps
mean,
actually.
that is really good. But then when you resin cast it, that means wouldn't you also, is the resin cast between high voltage and primary or on the outside of the high voltage?
No. In the 3D printed bobbin that you have, right? So between each layer, I added resin casts.
Ah, okay, like that. Okay, all right. No, that is good. Yes, that is definitely. And we also, instead of putting resin, essentially we put some kind of grease over the entire thing, and it also helped for us. But yeah, like we also thought about essentially dunking the entire thing in either oil or uh, essentially putting it in epoxy. But then what would happen was, if you put it in a insulation which has a non-unity permittivity, this epsilon not equal to 1 would essentially multiply with the parasitic capacitance. And for example, we tried it with oil, and then the output pulse again became a sine wave. So we had to use epsilon equal to 1. So it was either air or something else, maybe like SF6. But at that time, it is very difficult to procure and contain because you need a sort of vacuum chamber. Or so, yeah. But essentially, this was the entire workflow. So this took a lot of, I would say, 2.5, 3 months to go through. And there were a lot of failures. So we had, for example, Corona from the
Mostly the end ring failures, right?
which failures?
End ring. In the
Sorry.
transformer, we have the end ring, where where
Oh,
the
the end
character
ring.
is
Yeah,
done.
yeah, yeah.
Yeah.
Yes. Yes,
Same
I
problem.
completely agree. Yeah. It's good that somebody went through the same torture that I did. It makes me feel better now. um, but yeah, just like you mentioned, it was very complex. And actually, in my thesis, I won't go much into detail here because it would take too long. But in my thesis and also in our upcoming journal paper, I've essentially compiled all of the different failure modes that we could have when designing such pulse transformers. I observed a total of 5 failure modes and different kinds of solutions to essentially overcome these failure modes. And yeah, if you have more questions, we can take it later. But for now, let's say like there was a lot of failures, a lot of reiteration and redesigning. And also the worst part was when we would have a failure in the transformer, this surge transient would essentially travel all the way back to the pulse generator that I designed and even cause the switches to fry. So every time we'd have a failure, I'd also have to resolder the PCB. I also tried putting, like you say, like ferrite clips to limit the transient. I also tried Zener diodes, TVS diodes, a lot of stuff, but it was just inevitable. So yeah, but the main failure modes were essentially low voltage to the core, high voltage to the core, high voltage to low voltage. And then finally, these failure modes that we observed in the switches. And the final transformer looked something like this. So I ended up grounding the core actually. And we had the high voltage winding on top, and you can see like there is a lot of grease applied on it. And you can see here that the form factor is extremely small. And the reason for this was that we were limited in the cores that we could purchase.
Not only that, if you have a higher area, the flux linkage will be poor and it
Flux
will
linkage
cause
will be
poor
lower.
voltage regulation.
Exactly. So it is a very tightly constrained design. I would say if you move in any direction, there's always something that you're losing out on. But finally, we somehow made it work like this. And also, like you mentioned, the highest potential of the HV to the low voltage was a very severe design failure. So what I essentially did then was to concentrate the LV winding towards the bottom and kind of invert it, and also then use a silicon insulated wire instead. This was my 4-turn primary that was essentially concentric into the high voltage winding.
So in my design, what we did was in the high voltage winding, we added a lot of heat shrink tubes, and we again resin cast that end ring portion, and we
Right.
added a little what is that metal shields for the field uniformity.
Yes, yeah. No, that is also that's a really good solution, and we also tried something like essentially making the last turn sort of like a copper tube instead of a wire itself. But then you can see here that the distance from the grounded core is already so small. So when we try to put a sort of ring at the end, it then caused failures between that. Yeah, so yeah, a lot of designs have a lot of different approaches, and so this was the best that I could do, let's say, in 2.5 months. And finally, the winding, the transformer looks something like this in the CAD software. And I've compiled some design parameters. And finally, when seeing this, essentially, I could bring down the L sigma to around 730 micro and parasitic to 25 pico. And this was higher. So even after all of this optimization, it was still higher than, let's say, the really good pulse modulators, which are there for resistive loads, which again kept showing me how complex it is to design for keeping capacitive loads in mind. My final pulse modulator looked something like this. So obviously I had different systems also to not just the transformer. So we essentially took the 230-volt mains. I designed a small bridge rectifier, a simple bridge rectifier to charge up my DC link. This PCB I will discuss in the next slide. It was also a little complex to make. This PCB essentially is the pulse generator which makes the pulses out of the DC link voltage, which are then pushed into the pulse transformer, stepped up, is then going through the test elements, like I mentioned, the RT and the CT. The RT was implemented as a simple resistance bank, a high power resistance bank, that too, because it's extremely high, higher currents. And the variable capacitor was essentially like a disk high voltage capacitor, which you could like change the the distance between the two plates, thereby increasing epsilon A by D. And then finally the OIP sample. This I'll go into detail later how we set up the sample. We had the high voltage probe, and this part was also very important. This is what I call the disconnector or the breaker. So what this box essentially did was, after a dielectric breakdown occurred, it had to quickly disconnect the modulator from the mains. And this also required a lot of calibration. I'll show it in a future slide. So this was difficult to make. And then finally, we see the waveforms in these oscilloscopes. We can trigger them to actually capture the breakdown voltages and stuff like that. The PCB that I had to design was also a little complex because this can go quite high voltage, at least for powertronics, not for high voltage people. Let's say around 1000 volts DC. And what I ended up doing was using a 4-layer PCB. And what this, actually before I go, so this was essentially the AC mains part. And what would come out on the other hand is the pulses, and that would then go to the transformer. We have switches here, and they are individual high side, low side driving. Isolated supply for powering up both the sides of the gate driver.
Is this a resonant inverter?
No, it's a simple edge bridge. The
Okay.
reason why I used a simple edge bridge, and thank you for asking the question because I didn't mention it. This is actually a simple edge bridge circuit. And the reason why I did that was it is very easy to control frequency and also the shape of whether you want unipolar or bipolar very easily with such a PCB. So I didn't want to complicate it too much. This worked pretty fine. And So yeah, so I then designed this, and like I said, there were 4 layers. So there was the DC plus, so that had all the signals. Then the 2 layers for the output pulses, and then finally all the grounds essentially along with the DC minus. This is not DC plus, sorry. So yeah, and then this PCB worked fine. It took about a month to design, but was worth it. And the final wave shape looked something like this. And this was without the test elements, but with the test elements, it would look something like this. And here you can essentially see the power of having those test elements, because right now for the first test that we had to do, what was of interest to me was zero overshoot, fastest rise time. But in the future, let's say if we want to test something that is maybe closer to reality, because in powertronic converters, you do have a slight overshoot, let's say maybe 2 to 3%. And if you wanted to simulate that kind of overshoot, it's as simple as just changing CT. And then you can go back to something like this and then do a new range of aging tests with this kind of pulse modulator. And then measuring rise times for both 50 kilohertz and 10 kilohertz. I call it the bipolar and unipolar rise time. So the unipolar rise time was 1.84 microsecond, which satisfied the criteria of the 20% of the pulse width. So this was my final output pulses. And the thesis was still not over, because even after doing all of this, I still had the aging experiments to do. But now I at least had good looking pulses that I can apply across an oil paper capacitive sample. And then I went finally into the aging chapter of my thesis, which is the final chapter 5. OIP samples essentially stored in a vacuum oven. We would take out a bunch of them, immersed in oil still, for the tests, and then apply them one by one. The electrodes look something like this. There were 2 arrangements, a conical with a cylindrical, and both cylindrical, and we tested both of them for breakdown. I'll explain in the next slide. And here, when we didn't essentially dip them in oil, we can clearly see how there are some surface discharges when the oil started drying up. If you remember, I mentioned there was like a breakdown disconnector. So the thing is, when the breakdown happens, you're essentially short circuiting a current through the oil paper sample. And if you allow this current go on for too long, then you would have very aggressive burn marks. And this would cause a lot of these dots on the electrode, which would then have to be polished. And on the left side here, I took some microscopic photos to show that at 10 kilohertz and at 50 kilohertz, the burn marks were very different. And on top, we see this is with the detector and without the detector. So without the detector, you can see here that the burn marks were extremely aggressive, and this would deform the electrode a lot, which we believe that would affect statistics. So with the breakdown detector, we got, let's say, relatively better burn marks, but still we had to kind of polish the electrode after every test sometimes, or after every 5 tests. And then we essentially go down to the actual experiments. So this was the point of even starting this whole thesis, but then I had to go through this entire several months just to get to this stage. I did 2 kinds of tests. The first tests were breakdown experiments. So where I applied a 1 kV peak per second, it kept going up until the sample broke down. And this was done at 50 kilohertz. I did it for both the cylindrical and conical electrode arrangements, like I mentioned before, and saw that the cylindrical electrode has a lower breakdown strength. And this could be attributed to the fact that it is applying a more uniform electric field into the sample. So these were I selected the cylindrical electrode for the aging experiments that we did in the next after this. And these were the results of the aging experiments. So I know it's a lot of things on the graph, so we can divide it into we can analyze it slowly. So first, the diamonds are for the 10 kilohertz test. The circles are for the 50 kilohertz test. The cross marks essentially denote halted experiments, which probably went on for too long. And we felt that, okay, it is unrealistically long, so we stop it. But it's important to note that these halted experiments were also included in calculating the median point, because it is statistically possible that we had a healthy sample, like a very strong sample, and we have to consider that too. I then
You could have statistically removed the outliers by
yes.
using a Weeble or, but they are outliers, right? So you shouldn't include them in the median distribution. Calculating median.
Yes, there are two different ways. I could have, like, let's say, there is a sort of way to statistically negate these samples. But at that time, I just chose to include them in the median because,
Usually a 95% confidence limit is used to remove the outliers. So yeah,
yes,
go ahead,
yeah,
please.
yeah, yes. So, but yeah, thanks for the input. It is definitely possible. I've seen a lot of papers do that. But essentially what I did was then calculate the median at each field. I did a best fit line through these medians and then saw these final lines over here. Now, there were two major types of observations from this graph, and I want to go through them one by one. The first observation was the impact of frequency. So it is very clear that an increase in frequency causes reduced breakdown strength. And this is shown by the downward shift of the 50 kilohertz line with respect to the 10 kilohertz. The second is that an increase in frequency also reduces lifetime, denoted by the leftward shift in the 50 kilohertz line. And the cause of this, obviously, according to literature, it has seen that there are increased dielectric losses. But then also consider that the test object was in oil, which is a very good, which has very good thermal properties. So what we thought was then happening is that even though the overall temperature of the sample is not increasing, due to the non-homogeneity of the paper fibers, an increased dielectric heating could cause local hotspots, which would first cause local thermal breakdown and over time global failure of the complete insulation. This is what we thought was the reason. I took a small snippet out of the paper that we are writing which explains this in further detail. And the second kind of observation, which I found very interesting, was the impact of field. Now, if you look at the 50 kilohertz line, you can see that around between 20 to 21 kV per millimeter, there is a transition. And it looks like the lifeline is essentially slowing down below this critical field value. And I did a lot of reading in the literature to see similar bends, and I found two of them. I think this was first was Wei Jun Yin, I think in 1997. She showed that this level could essentially be the partial discharge inception voltage level, above which partial discharges greatly accelerate the aging, but below which don't happen and they don't accelerate aging, and this could cause a slowing down of the lifeline. Also, back in, I think this was very long time back, I think in 1930s or something, there was, or maybe 1800s, in fact, also, there was a man called J.P. Krein in Baden, ABB. He essentially studied the surface charge injection in polyethylene. So it's not for oil paper, but he did predict a critical field value of around 21 kV per millimeter, which is very interesting. And it could be just a coincidence, but I still have to delve deeper into, is there more into this correlation? What we came up with the cause was for this line was essentially that there could be some, so if you see the paper fibers of the OIP itself, there could be oil-filled cavities that exist within the paper fibers. And this FC is essentially the inception level of these small cavities because they would have field enhancement. And if you go above it, it would cause faster failure. And if you go below it, it would be slower failure. But yeah, this was essentially my entire master thesis. It kind of ended a year. There's obviously more, and the thesis is under embargo at the moment, but soon it will be out of. And if you're interested, you could definitely go through it. There might be some learning experiences that you could take from it. There'll also be a journal paper. We already have a conference paper. There'll be a journal paper coming up. But to wrap it up about my thesis, and also, Pratisha, should we take a break sometime, or I don't know if what?
I think you need to be freed by 4:30, right?
Yeah, okay. So we just keep going on. Yeah.
Yeah.
And
Otherwise,
how?
if anybody else has any questions in the audience, they can ask if you want a
Sure.
short break.
Yeah. Then maybe I just finish off this slide, and then we can take a small 2-minute break if people need.
Okay.
But essentially, to summarize my outcomes from my thesis. So if you see on the right side, like this was sort of this is basically a plan of my entire thesis that I chalked up at the beginning. And you can see there was a lot of different different aspects of my thesis that I had to explore. The technical outcomes were that I learned that developing pulse transformers, pulse modulators for capacitive loads is very complex. It is not as easy as replacing the resistive load with a capacitive load. The capacitive nature of dielectrics inherently complicate the design criteria. We also saw a decreased lifetime of dielectrics at higher frequencies, as was already seen in literature. So I don't think that's something new. But what was interesting here, and I wanted to explore it further, is that if you take a sine wave at, let's say, 20 or 30 kilohertz, and you take a pulsed wave at the same frequency, would there be a difference in aging between pulsed waveforms and sine waveforms? And if there is some deviation, then that means that that deviation is purely related to the rise times. And that was some, yeah, exactly. So that capturing the impact of that dV/dt on the dielectric aging was also something I was interested in, but obviously I just have 9 months, so I can't explore it. But hopefully in the future, I see more papers about it. And I hope that this kind
So
of,
you can do a switching impulse, to see if the effect of rise time.
yes, yeah, you can do switching impulses as well. Yeah. You mean repeated switching impulses or just one switching impulse?
No, repeated switching impulse
Yeah,
to.
that is correct. Yeah. Yeah. You can do that as well. Then that would, I think there are some papers that already explore this, because from my literature review, what I saw is that around 1990s is when they started researching the impact of these rise times and overshoots, because that was also the time, I think, when these variable speed drives started coming for motors. So power converter fed motors. And then they saw a lot of failures in the windings of these motors. And then they were like, okay, we haven't seen these before. And then they essentially did a lot of research on the impact of rise time. So I think there's a lot of literature there. So yeah. And also then the most interesting for me, I would say, is this deviation in aging below this critical field. And obviously we are still working more on it. My professor's doing more. And one thing that we are also trying to do is essentially have another line at 30 kilohertz, and then see if this FC value is the same for 30 kilohertz or it's different. If it's the same, that means this FC is a inherent characteristic of the OIP sample. But if it's different, that means FC essentially depends on the frequency of sorts. And that would also be a very good clue into what exactly this critical field is. On the personal side, I think the thesis taught me a lot of things. The most important thing I would say is, if you look on the right, like we see a lot of interplay between high power and high voltage. So we had a lot of high voltage statistics towards the end in the aging experiments chapter, but the pulse transformer itself was a combination of designing high power electronics, keeping high currents in mind, no longer milliamps, but also at relatively higher voltages, which can go up to like 15, 16 kV peak to peak. And this kind of intersection between the two fields really excited me at the time. And that is why I wanted to delve deeper into that, as opposed to just powertronics or just high voltage. And I also then found out the importance of front loading. And if you see again on the right, I kept the work very big. And then later on, it was easier for me to limit my research scope. But I found it more difficult to expand my research scope, starting with a smaller scope, than to limit a bigger scope into a smaller scope. I hope that makes sense. I also learned that after all the repairing I had to do for my PCB, like if nothing else works in life, I can at least start a PCB repair shop. So yeah, so there's always a backup plan, I guess. And the final section that I'd like to talk about is my work here at Hitachi Energy. But I think, Pratish, should we take a break? Or if people feel like they can keep going on, then. Hello?
You're audible.
Uh,
You're
Yeah,
audible.
sorry. Yeah, hello.
Yes. Should we keep going on? Or how am I doing on time? Like, because I have not actually.
You are, it's 4 IST now.
Okay, all right. And we go till 5 IST or 4:30
Uh,
IST.
you have a lab work at 4:30, right? That's what you
Yes,
told.
but I can push it just a bit more. That's okay.
Okay.
So maybe I finish off the slides then, because these are not so many slides left. And then
Okay.
we can go to the questions.
Okay, sure.
All right. So the final section that I'm talking about is the major experience that I'd like to share with all of you is my R&D work here at HVDC, at Hitachi Energy. And the first thing I'd like to talk about is the place that I'm at. I don't know if a lot of you have heard of it, but maybe a lot of you have. It's called Ludvika. It's in Sweden, and it is considered by many as the center of many high voltage technologies. And this is essentially a picture that I've taken from another colleague, but it shows that it's essentially a mega city, which is just centered around high voltage. So we have all different kinds of components like bushings, transformers, reactors, surge arresters, breakers, and you also obviously HVDC converters where I work. We also have different kinds of labs. We have the high power lab. We have testing of different stuff like transformers and breakers. We also have STRI, STRI. I don't know if a lot of you have heard of it, but it is essentially a third-party high voltage testing consultant. And they also do testing of cables. They also do testing of converters, a lot of different stuff. So essentially, what I'd like to say, if any of you have the chance of just visiting Ludvika, please do. I think it's an excellent experience to come here and see the kind of innovation that is happening all in one place. So yeah, and if your SBC chapter is interested in setting up some kind of study visit, you can always contact me and we can try to find if something is possible. Because after coming here and spending almost 2 years, I believe more people should see this place. It is very exciting for high voltage people. All right, well, enough about Ludvika, but what do I work on? Well, essentially, we know the figure on the left. I mean, we've seen it in a lot of textbooks. Essentially, two AC networks, some kind of conversion, AC-DC, DC to AC conversion, and we have a DC link in between. But we always have this kind of box over here. And not a lot of people know what this box is. It's just something that converts. But what this box looks like in reality is something like this. And this is what we call a HVDC valve, analogous to a mechanical valve. Semiconductors on the electric side essentially switch on and switch off, and we can use this in different topologies like MMC topologies to essentially produce AC or produce DC and do a lot of cool things with it. I perform R&D of these this system basically, and I can briefly talk about what my workflow look like. And my workflow is essentially, I would say, three major parts. One is semiconductor device physics. I have high power design and testing, and also high voltage design and testing. So designing a complete valve starts at the semiconductor level. And when you think of semiconductors, usually we think about these MOSFETs that we put on PCBs, but this is not the semiconductors that we use in HVDC. As opposed to the 1200 volt 50 amps, I'm sure there are different combinations. The ones that we use in HVDC can go up to 5,000, 6,000 volts and 10 kiloamps switching. So that is a massive amount of power that is flowing through one device. And on the semiconductor level, I essentially do a lot of double pulse testing. Maybe some of you recognize this setup, but essentially looking at the turn on and turn off waveforms of semiconductors and optimizing the gate drive to reduce stresses on the device. And here I'd like to mention that high voltage physics actually helped me a lot here, because understanding what really stresses a semiconductor is somewhat similar to what stresses a dielectric. And the field, the setting up of field, the dB/dTs, it was very similar. I could essentially draw a lot of parallels with my high voltage lessons back in Delft.
Philip, one question
Yes.
there. So that setup, is that automatic turn on? Because both the what I usually do when cascading switches is that I use a floating. I use a floating gate driver.
Yes. Yeah.
So, but you've used the cascade in this way, which means if one turns on due to dV/dt, another one will turn on. Something like that.
Okay. First of all, which are you talking about, this setup?
Yeah, that's it.
Okay. So, I'll two answers. The first answer is yes. When you have series connected semiconductors, you need to kind of harmonize their switching on and switching off.
Mhm.
And we do that in HVDC depending on the topology. Right now, we are in the MMC era, I would say. MMCs don't really have this kind of series connected devices, so they don't have those issues. That's the first answer. The second answer related to this circuit, this is a double pulse circuit. Two switches are never on at the same time.
Okay.
But what essentially this does is you turn on one switch and you charge this load reactor to a certain current. And then you switch off that switch and you turn on the DUT, and you make the DUT switch on at that current IL. And that is essentially testing the turn on and turn off of a certain device. And this is a widely used, I would say, circuit. It's called the double pulse test to study semiconductor behaviors, especially transient switching behaviors. But then once I have the semiconductors tested and optimized, I then move on to the converter side. So we then build up these converters. So this test can happen at, let's say, a few kV. So it can go maybe up to, I would say, 4 kV, and it can go up to 10 kiloamps. And then we go into the high power testing, which is essentially testing the entire converter. And this can go very high. You can have 15 kV. I would say up to 5 kiloamps or even higher. It can go sometimes even to 8 or 10 kiloamps. So it's a massive amount of power. And we have, this is just one of our labs, but I can't show you a lot of stuff because of confidentiality, but we have massive labs that can supply a lot of power pumping in through the converter. And then we do operational and control tests. So operational tests to check if we actually essentially replicate an HVDC station in the lab. And then we check if the control system is working correctly. We go through different kinds of control operation areas. And the major standards that we use here are the two HVDC standards, 62927 and 62501. 62501 is for HVDC, 62927 is for STATCOM valves. And then once we have tested the high power part, so the entire converter topology, we go into the actual high voltage design. So it's the mechanical design of the entire valve that is extremely important because the final HVDC station operates up to like maybe 800 kV to 1,000,000 volts. We can't take any sort of failures. I would like to mention that the main dielectric, the primary insulation in HVDC valves are usually just air. So there's no oil anywhere because of a lot of different factors. Again, with the same two standards, we have different kinds of tests. We have AC tests, pure AC, pure DC. We have AC superimposed on DC because in HVDC converters, we have DC on one side, AC on the other, and this can cause different sorts of voltages in the valve. We also have lightning impulse and switching impulse, very similar to how we do it in cables. And this can go up to very high voltages, obviously with low currents, but yeah, extremely high voltages. And this is one of our high voltage labs. We have, I'm not sure how many total, maybe 4 to 5. And over here in the middle, you can see it's essentially a classic thyristor valve that is being tested. And we have all different kinds of tests that we perform on this. So yeah, but this is essentially my entire workflow. And what really excites me here is that there is a wide variety of what I can learn. So on the semiconductor level, I still have high power electronics at the converter level, and I can also still use and leverage my high voltage knowledge from Prysmian and from Delft to assist me when I test and understand high voltage testing of valves as well. I also did some other activities. I'd really like to mention here this IEEE summer school. It's a DEIS summer school. It's done once a year. And I think a couple of the attendees were probably my co-attendees. This was an excellent opportunity to network with fellow PhD and R&D professionals. And if any of you have the chance to go for it, I would highly recommend taking part in it. The application process is simple, and hopefully maybe you can get funding from your college/company. I also, so the conference that I went to was Nordis, the Nordic Insulation Symposium in Trondheim, NTNU, Norway. And then we also got to see the Sintef high power and high voltage labs, which is very interesting. Within my company also, I got to travel to sister branches. So we have our semiconductor fabrication facility in Lensburg. It's a massive facility which produces semiconductors for various things, not just for HVDC, but also for e-mobility, for medium voltage power converters, a lot of stuff. And also we had a session in Krakow, which is in Poland, where we have our Powertronics R&D facility. The reason I mention these two is also because if you have any interest in working in something related to this, please let me know. There are a lot of opportunities nowadays, so I can definitely connect you with the right people. And then finally, also I'm also a board member of the Sigre NGN of Sweden. We started it just last November, and we also had our first webinar and a study visit. You can check it out. Yeah, and this is essentially my final slide, just some reflections. Obviously, I'm not very experienced, so I don't want to give advice to anybody. I don't believe I'm there yet, but I can tell you what I've learned from my experiences so far. The first thing is about balancing two mindsets. I am a researcher. I like academic research because it's boundless and you can explore. But then spending a while in the industry, I also realize it's important to balance these both mindsets. To have, on one hand, you should have the curiosity to explore, but on the other hand, you should also kind of be product centric or cost oriented. So a little more defined research questions. And the second thing, which is actually the topic of this webinar, I am seeing a major boom in combining high voltage knowledge and high power electronics, because the energy transition is essentially increasing is making power electronics creep into the high voltage and medium voltage area. And power electronic engineers by themselves don't have a knowledge in high voltage, so they don't maybe understand how breakdown works or how things can fail from a dielectric point of view. So in a lot of the conferences and events that I'm attending, I'm seeing that having high voltage expertise in the high power domain is extremely important nowadays. And I can foresee a growing need of such expertise. And also the last point, which is essentially a lot of support from others. Obviously, whatever done is only because of support from others. So if there is something that you are interested in, and if there's any way that I can help, please reach out and can set some sort of collaboration up or research together, and it would be my pleasure. So yeah, but that's basically my talk for today. I tried to cover a lot of different things. I'm sorry if it was a bit overwhelming, but yeah, I think we can take some questions now, and I have to leave after a bit, but I think I can stay for a bit longer. So yeah, I have my number at the bottom and my email in case you'd like to reach out. Yeah, I think we can take some questions now.
Yeah, thank you, Philip. The floor is open to the audience to ask questions. In the meantime, the talk was really very detailed, and it was very nice to hear all the experiences that you have shared, starting from the master thesis, then your work at Prismium, and your recent works at R&D Hitachi.
Thank you.
So again, Balaji here.
Hi, Balaji. Yeah.
Sorry for bothering you with a bunch of questions.
No, please. I'm actually enjoying this a lot. Like,
Okay, yeah. So the thing is, next time you're going to CERN, right?
yes.
And the situation is kind of different. They use superconducting magnets there for this thing, particle acceleration. So how do you think the power electronics and the high voltage phenomena will change in such superconducting environments?
That's a really good question. Short story, I don't know yet because I've not gone there, so I don't really know, but I would love to. We can definitely keep in touch, and I'll tell you more about it once I'm there. But I'd also like to highlight that it's not just the magnets, it's basically the converters themselves that are experiencing this high power, high voltage intersection. So designing these converters themselves is not as simple as, let's say, taking a power electronic topology, writing what the voltage waveforms are like, and then just designing it. But designing it, I feel like in the development stage, having this high voltage expertise, what I have seen, massively helps with a lot of different issues. So yeah, that is the kind of intersection that I'm excited about exploring at CERN. But yeah, if I get to know more about the impact of such waveforms, even on the superconducting magnets, I will be sure to let you know as well. So we can keep in touch with it.
Great, thanks.
Yeah. And thanks a lot for the questions. It was good to know somebody else suffered designing pulse transformers. Yeah. So yeah, okay.
So I usually switch to the solid state Marx topology. That's better. It doesn't have all those ringing, and it's a lot of when more energy storing components are there in the system, it's more chaos.
Yeah. I'd love to read more about do you have some papers published on it that I can go through, or maybe some?
No, I didn't publish, but I mean, I'm still working on that side by side.
No
but
worries.
I did publish one. It's in IEEE. I'll share you.
Yes,
it's
please,
on
yeah.
DC polarity reversal. It's pretty much this. It's very similar to what you've done in masters, but instead of high frequency repetitive pulse, it's just single pulse, positive 11 kV to negative 11 and negative to positive. How DC polarity affects the breakdown in polypropylene. So
oh wow,
I can send you the link.
Yes, please. Yeah, I'd love to read it. I think that's.
Yeah, Philip, I'm Dr. Tirumurugan.
Hello. Hi,
yeah. So I'd like to ask you why you choose uniform field instead of needle plane electrode.
Okay, that's also a good question. Maybe if I can go back. So so there are two reasons actually. The first reason is obviously that under a uniform field, I felt that studying the impact of the frequency is more pure, let's say. So we are negating any other impacts that the electrode arrangement might have and studying only the impact of frequency. So that was one reason. And the second reason was that since my pulse modulator was already limited in voltage because of all of the challenges that I spoke before, having a lower breakdown strength allowed me more testing capabilities. So because this breakdown strength was low, I was able to go to very high fields here at 10 kilohertz also. Which might have not been possible because then I would start getting flashovers in my transformer, other failures.
Okay.
So, yeah.
So oil and bird, so cellulose and which oil you used? Mineral?
Yes, yeah. I can share the date, not the data sheets, but the names in the chat. I can send it to you after that. Yes, thank you.
Okay. So it's nice talk, Philip. We really enjoyed.
Thank you so much, sir. Thank you. Means a lot. Oi. Okay, I think I just removed my entire.
Hi, this is Aniket. I would like
Hi,
to
Aniket.
ask one question.
Mhm.
Which software do you use for high power design and testing?
Okay, that's a good question. So maybe if I can just, sorry, I just need to share my screen again and really go down to the very end. Sorry, just give me a second. Okay. So at which step are you referring to? You're like, you mean in the middle step?
Yeah.
So the middle step, essentially, we use a variety of different softwares. Mainly, I would say it is MATLAB and PSCAD. We also, so in high power, in an HVDC converter, it's not only the voltages and currents that are of interest, it's also the cooling, because cooling is a very, very important part, if not one of the most important parts of the HVDC valve hall. So we also have thermal models in MATLAB that allow us to predict what kind of junction temperatures and cooling water temperatures we would reach. So to answer your question, I would say MATLAB, we have some other, let's say, applications that we have built in MATLAB, which are Hitachi patented, and then also PSCAD we use. So that is the two major
Okay.
software.
Thank you. And I have one more question.
Yes.
Can you suggest some fine literature or books or textbook on high voltage physics? Because there are a lot of research paper, but I didn't found any major book on high voltage physics which deals with all the phenomena involved.
Okay. I mean, my go-to suggestion is always F.H. Krauger. He was a previous professor at TU Delft, so it was pretty much our Bible when we were doing our masters there. So I have learned almost everything I know from. He has 3 books. The third book being on HVDC. I've learned most of my stuff from those books, I would say. There is also another German book, and I can try to find it and send you the photo. Send you the title of it, or maybe even the PDF.
Okay. And from which publisher?
It's a German publisher. I will find it and I'll send it in the chat because it's there in my. Yeah, I have to find it. I'm really sorry I don't have it right now, but for sure I will send it to you. Maybe you could just send me an email and then I can reply to that.
Okay, thank you. I will send an email.
Yes, all right.
Hi, Philip.
Thank you for the question. Hello, hi.
Hi, am I audible?
Yes, you are.
When you designed your whole setup with certain RT and CT and so on, you probably would have taken the capacitance of the sample. But if we if we are planning to test different samples, you'll find the thickness changes and the capacitance changes. So the wave shape also would change accordingly, you know.
Yes. Yeah.
So in the design of the component, you know, do you need to make I mean, have you thought of making that kind of changes, or you were testing only with the in a uniform thickness samples?
Yes, that's a really good question. And this was also something that I tried exploring essentially. And you're basically saying something like this, but for the thesis, I only tested single layer YP samples of, I forgot the thickness, but if we were to go to double layer or triple layer, or even change it to, let's say, an epoxy, and this is something we tried, the epsilon would change, the C load would change, and the waveform would again change. But because we have the RT and CT variable, we can again tune back the waveform to what we want. And that kind of flexibility in the future would allow us to test different layers, different materials, all at the same wave shape.
Oh,
And that is what I feel like a very, very important part of building this modulator, because we need repeatability.
right.
And that is extremely important in statistics. And I'm really happy that you mentioned that. So thank you for that. Yes.
Thank you. Thank you. Good. Very good.
So with the same test circuit, you can't do unipolar, right? Or if you wanted to do unipolar, the pulse frequency should be very, very low.
Not necessarily. The only change, at least that I can think of, to do unipolar would you have to introduce a reset circuit into the pulse transformer. And this has been studied by Dominic Portis and Jürgen Biela from ETH. They have a optimized DC reset circuit, basically, so essentially we have the primary winding and the secondary winding, and they also have a tertiary reset winding. And this is kind of controlled by a microcontroller. And every time they essentially estimate the core saturation. And after a certain point, this winding would turn
They
on.
turn on the tertiary to mitigate the saturation.
Exactly, in the opposite direction. So the only change I see that would need to be implemented to allow unipolar testing here in my setup is essentially this reset circuit. And maybe some few tweaks in the Arduino. But I think apart from that, it should be good to go.
Okay, great.
Hi, Philip. Am I audible?
Hi, yes, you are.
Hi, this is Shreya. Thank you so much for the wonderful talk. I wanted to know from your experience, you've mentioned the things we could do to reach to be where you are. Are there any things that you suggest are absolute no-nos or things that we could avoid from your experience?
Yeah, okay. Thanks for the question. I think that's like I said, I don't want to seem like somebody who is giving advice, because I myself am still learning a lot. I'm still early in my career, but still I think that's a very valid question. Some of the things I considered no-nos are, I have noticed sometimes that we as researchers can get too zoomed in into what we're doing. And throughout my thesis, I felt that taking a step back and just giving myself a second to really understand, like, okay, what am I doing? And is this small aspect even important in the grand scheme of things? It has helped me a lot because, for example, in the pulse transformer, as a very good example, I was so like, my research brain was like, no, I want to optimize it as much as possible. But then 2.5 months in, my professor told me to take a step back, and we already have a pulse waveform that is capable of testing dielectrics, and we can already finish the thesis now. So further optimization would give marginal return. And I think that is one thing maybe that I could mention here, that sometimes we get too engrossed in optimizing something. Take a step back at a point and see, like, is this really necessary? Can you move forward in your research? Because I find that moving forward in your research is much more important sometimes than going extremely deep in every single aspect. So yeah, I would say that is one aspect, but obviously it's very context dependent. But yeah, I hope it brought the point across. So
Thank you. Got it.
thank you.
I think we can take up more questions through the email ID and phone number
Yes.
that you have shared.
Yes.
So I would request all the participants, if possible, to switch on their camera to take a group photo in form of a screenshot.
I just need to comb my hair before the screenshot. Maybe a bit. Are you taking the screenshot or is it done or?
I have taken one. I'm waiting if anybody
Yes,
else.
yes. Yes, it is done, Britta, sir.
Okay.
So thank you again, Philip, for this presentation. It was quite interactive, and with that regard, I would kindly ask you to accept the virtual token of appreciation on behalf of IEEE DIS Student Branch Chapter IIT Kanpur.
Okay.
Team, please share the token.
Is that coming in the chat or where do I look?
No. It'll
Oh,
come.
wow. Okay. That's so cute. Okay. Thank you.
Yeah.
That is very sweet. Thank you so much. Yeah, I'd really like to thank you for having me on this talk. It was a bit hectic and I know we had to change the dates a lot of times.
Yeah,
So
I
thank
know.
you for that.
It's okay. I am happy that we could manage you well within this, because most of our team members are leaving today and tomorrow.
Right. Yeah, you mentioned.
Yeah. Okay. So with this, I would like to acknowledge the efforts of the IEEE DIS SBC team, IIT Kanpur, for planning this wonderful webinar. I express my sincere gratitude to IEEE IIT Kanpur student branch and IEEE UP section for their support, and acknowledge Dr. Alok Ranjan Verma, our faculty advisor, and Dr. Nandini Gupta, our mentor, for providing their valuable guidance. No event is complete without a lovely audience. We thank you all for being part with us. Thank you. It was a great pleasure, and thank you very much, Philip. We would definitely have you again. We would definitely like to know the details once you join CERN. I think you'll have more to share. So thank you.
Yes, for sure. All right.
Great
Thank you.
having you, Will.
Thanks a lot, Balaji. I'll talk to you.
Sure,
about
we'll connect,
things
yeah.
as well. Yeah, we will connect. All right. Okay. All right. Have a great day and I shall get back to the test center now.
Yeah,
All right.
sure. Go ahead. Okay.